Alright, so one of the movies that I watched when I was younger, I really liked, and it's kind of stuck with me, one of my favorites, is Indiana Jones and the Raiders of the Lost Ark. So if you have seen it before, you might recognize in the beginning there's a scene where he's running, and there's a giant boulder that's rolling after him. Okay, so we're going to kind of recreate this scenario, and let's say that this boulder is rolling towards him. Let's say it has a mass of 1,500 kilograms, and he's running just fast enough to get away from it. So we'll say that his velocity is 4 meters per second, and so the translational velocity of the boulder would also be 4 meters per second. Okay, but before we solve it, let's just get some context real quick. Okay, so now that you have an idea what I'm talking about, let's go ahead and find out, well, how much energy did that boulder have? And energy is kind of a measurement of how much damage it could cause. Okay, so we're going to figure out how much damage that boulder was capable of causing by finding how much energy it had in the form of kinetic energy. Okay, and so this will be kind of serve as a sample problem example for us as far as the kinetic energy of rolling. Okay, because a rolling object has two forms of kinetic energy. It has rotational kinetic energy because it's rotating, but it's also going to have translational kinetic energy relating to its velocity, the velocity of its center of mass. Okay, and the big assumption we can make is that it is rolling without slipping, because if it's rolling without slipping, we can say that V is equal to omega times R. Okay, which means that omega is equal to V over R. Okay, so anyway, let's go ahead and calculate the kinetic energy of this boulder. Alright, in order to do so, we need to know what its moment of inertia is, and then we can replace omega with V over R. And again, the reason we can do this is because it's rolling without slipping. Okay, so the speed at which it's translating corresponds to its angular velocity with this equation. Okay, what we're going to say it's a uniform sphere. If you look in your table, that's 2/5 mr squared. Okay, and so we're going to plug it into here, so we get 1/2 times 2/5 mr squared, okay, times V over R squared plus 1/2 times m times V squared. Okay. So we do a little bit of math here. We'll simplify this to get 1/5 capital MV squared plus those r's cancel, the v gets squared, the 2's cancel, plus 1/2 MV squared. Okay, 1/2 and 1/5 are going to be, let's see, 5/10 plus 2/10, so 7/10 mv squared is equal to the kinetic energy. Okay, so that would be 7/10 times 1,500 kilograms times a velocity of 4 meters per second. We're going to square that. Okay, and we get that it had about 16,800 joules of kinetic energy. Okay, which is a lot of energy. It's a big old boulder. Okay. Alright, and I think I'm going to have you guys practice one now. So let's go ahead and we'll save this. Let's come up with another problem. Okay, so this will be our next scenario. Pay attention because it's going to happen really fast. But this is an art exhibit that got away. Okay, it's a big giant red ball. And it kind of just took off down the street. Okay. We're going to say, though, that it is it looks like it might be, I wonder if it's filled with air. It says 250 pounds. Maybe it's not filled with air. It looks pretty soft, though. Okay. Anyway, we're going to analyze this situation. Find how much energy that ball had. So that ball had a mass of about, well, it was 250 pounds, so that would be a mass of about 110 kilograms, okay? And they said its radius was 15 feet, or its diameter was 15 feet, which means it would have a radius of about, say, maybe like 4 meters, or 2.5 meters. Yeah, we'll say a radius of 2 meters. Probably a little bit more than that, but we'll say 2 meters. And let's say that it was rolling along. I mean, they had to run pretty quick to catch it, so maybe like, and it was definitely outrunning them or getting ahead of them at one point. So let's say it was going at the fastest 8 meters per second. Okay, so what I want you to do is find the kinetic energy of this rolling ball. Okay, and for the sake of this, we're going to say that it was hollow. Okay, that it was filled with air. I don't know if it was or not, but assuming that it was, then the moment of inertia would be, instead of 2/5, it would actually be 1/2 mr squared. Okay, so given that, and assuming that it's rolling without slipping, which means that V equals omega times r, go ahead and find the kinetic energy of that ball. Okay, so total kinetic energy would be the sum of the rotational kinetic energy plus the translational kinetic energy. Moment of inertia is 1/2 mr squared for a sphere, a hollow sphere. V over r squared plus 1/2 mv squared. Okay, this will all simplify here to 1/4 mv squared plus 1/2 mv squared, giving us 3/4 mv squared. Okay, which is 3/4 times 110 kilograms times 8 meters per second squared. Okay, so that would mean that this ball has 5,280 joules of kinetic energy. Okay, it was going about twice as fast as the other ball. Okay, but since it had significantly less mass, and that mass was all, well, since it had significantly less mass, then it has much less kinetic energy, about as third as much, I believe, energy as the previous one. Okay, so there we have the kinetic energy of rolling.